Section 5.1 Antiderivative and Indefinite Integration. By the end of this section, you should be able to find the general solution of differential equation and use indefinite integral notation for antiderivative, and find the antiderivative using the basic integration rule, and eventually find the particular solution. So the differential equation here, it means, let's say you have a function whose derivative is equal to 2x. For example, this is an example of differential equation. Whenever you see an equation with a derivative of some function, that type of equation is called differential equation. And our goal here to find out the general solution of this differential equation, and at the same time, finally, particular solution. And that's what we're going to discuss in this section.
So antiderivative means actually it's the opposite of derivative. So for example, let's say you have a function, one function, let's say x squared. Let's say name of this function is capital F of x. And then if you try to find out the derivative of this function, then the derivative of this function would be 2x. Now antiderivative of this 2x is going back process, which is x squared. Okay, so antiderivative of 2x is x squared. Okay, so a function capital F is an antiderivative of small f. So in this case, the small f is 2x if the derivative of this function is 2x, in this case small f. Okay, so but if you look at another case, let's say g of x, which is x squared plus 5. Now the derivative of this function g of x is also 2x. So as you can see that if you go back, meaning going back process, so going back process of the derivative is called antiderivative. But in this case, the antiderivative of 2x is x squared plus 5. So the antiderivative, you might have more than one answer. Actually, you might have, you have infinite answer for the antiderivative going back process. Okay, so that's the reason what we say the antiderivative of any function is if capital F is an antiderivative of small f, then the most general antiderivative of small f can be written as this way: capital F plus some constant. That constant could be 0, could be 1, 2, or could be any real number. That's why the antiderivative of any function, you might have infinite solution like this. So these are the collection of some of the derivative and going back process. For example, if you try to find out the derivative of x to the power n by using the power rule, it would be x to the power n minus 1 over n times x to the power n minus 1. That's the derivative. But now we're using the very same fact, but because we're doing opposite, reverse, so antiderivative of this one would be x to the power n. So why is that? So to check that thing, try to find out the derivative of this expression. So you can see that derivative of this expression is 1 over n plus 1 times, the derivative of x to the power n plus 1 is n plus 1 times x to the power n by using the power rule. So it gives us x to the power n. So now, we can collect all these, antiderivative for different known function. So what is the antiderivative of sine kx? K could be any number, okay? It's a negative 1 over k cosine kx plus c, because the derivative of cosine kx is actually k times negative sine kx. Okay, so whenever you try to find out the derivative of this column here, it will be this one. That's why antiderivative of these functions are this thing. So after doing a couple of examples, couple of problems, you will be able to remember this thing. So it's there is a direct relation between the derivative and antiderivative. So when you try to find out the antiderivative, try to think of a function whose derivative would be that particular function you are looking for, and then just add plus c. Okay, so whenever I need this table, I'm coming back here and then try to use this table. Okay, so there are two things we can use here. One is if there is a constant times function, and if you want to find out the antiderivative of this, that is actually constant times the antiderivative of the function plus another constant. And if you have the sum or difference of the function, their antiderivative is actually sum and difference of the antiderivative of this respective function plus some constant. This c only represents for some constant. So in general, so because we know that there are infinite antiderivative of any function, so all those collection can be denoted by using this notation, and that's called integration, indefinite integral. Okay, so this is actually collection of all the antiderivative of f of x. So the collection of all antiderivative of f is called the indefinite integral, of f with respect to x, and it is denoted by this symbol here, you see here, that's called integral sign. The function f is the integrand, which is you are trying to find out the antiderivative for, and then x is the variable. So whenever you see this symbol, that means you are trying to find out all the possible antiderivative of this function f of x. Okay, so this is just a notation, like we used to use d over dx for finding the derivative. Now we use this integral notation for finding the antiderivative, but this notation means all the antiderivative, so you always have plus c. Okay, plus c in the answer. I'm going to show you a couple of examples here. So find the antiderivative for each function when c equals 0. So you get answer in terms of c, and then you plug c equals 0. So if you go back here, if you use the first formula, whenever you see x to the power n, here, so the antiderivative of g of x, which I'm going to write it down as integration of g of x dx, is equal to -8. I can keep this -8 outside, and because this n is -9, 1 over -9 plus 1, that's the formula, that's coming from the formula. If you remember, antiderivative of x to the power n dx is 1 over n plus 1 x to the power n plus 1 plus some constant. So it's just a reverse of the derivative. In the derivative, we just multiply n times x to the power n minus 1, but in the antiderivative, you divide by n plus 1, and then the exponent would be plus 1. So here in this case, it would be -8, it's coming from here, and then n is -9, so n plus 1, which is -9 plus 1 times x to the power n plus 1. So here, as you can see, that there is a 8 on the top, -8, there is a -8 on the bottom. So x to the power -9 plus 1 is -8, and make sure that because this c is equal to 0, that's what we have given. So this is plus 0, you don't have to write down the c. So if you simplify this thing, it would be x to the power -8. So this is the one of the antiderivative. When c is when c is 0, this is the only one antiderivative for this function when c is 0. So that's how we find antiderivative of all these different function here. So for this one, we can use the same trick here. So antiderivative, I can say antiderivative of h of x is equal to, it's 1 over n plus 1. In this case, it's a 9 plus 1 x to the power -9 plus 1, and I don't have to write down c here because c is 0, it's given. So it will be -1 over 8. This negative is coming from here, x to the power -8. Okay, I can write down this as a -1 over 8 x to the power 8. I can always make it positive exponent if I want, if needed. So that's the antiderivative for the second one. For the third one, antiderivative is antiderivative of this function, and then 3, and then plus c. But because c is 0, so just use the power rule for the first part, second part, and then for the third one. For the constant, if you look at the constant, if there is any constant, because for the constant n equal 0, that means the antiderivative would be just x. Okay, there is any particular thing here? No. So if you want to find out the antiderivative of some constant, then that would be that constant times x. That's what we have to use here. I'm going to rewrite this thing problem here in next page. Kx is equal to x to the power negative 9 plus 4 times x cubed plus 3. So antiderivative derivative of kx is antiderivative of this one, which is 1 over negative 9 plus 1 x to the power negative 9 plus 1. I'm using the power rule. Plus antiderivative of this is 4 times 1 over 3 plus 1 x to the power 3 plus 1. I'm again using the power rule. Plus the antiderivative of 3 is actually 3 times x, and then plus constant plus c, but in this problem we have given that c should be 0. So now let's just simplify this. This is x to the power negative 8 over negative 8. I'm going to write down that negative here, plus it's a 4 over 4, which is 1, x to the power 4 plus 3 times x. So that's the answer, negative 1 over 8 x to the power 8. I'm bringing this negative exponent to the positive. This is x to the power 4 plus 3x. So that's the antiderivative of this function when constant c is 0. So let's go to another problem. Here we are just trying to find out the general antiderivative, meaning finally after finding the antiderivative of each of these functions, we just put plus c. So by using the very same idea, by that power rule, x to the power negative 9, that's the first one, x to the power positive 9 minus 1 over 9. By using the power rule, for the first one it would be 1 over negative 9 plus 1, x to the power negative 9 plus 1. I'm using this one. Antiderivative of x to the power n is 1 over n plus 1 x to the power n plus 1 plus some constant. I can use this formula for any n except n equal to negative 1. Okay, so here because n is negative 9, so I can use the very same formula. I can use the very same formula for the second part, which would be 1 over 9 plus 1 x to the power 9 plus 1, and then this is the constant, so it's a 1 over 9 x. If you are looking for the antiderivative of constant, that would be that constant times x plus c. That c represents for the indefinite integral. That's the general antiderivative. So here it would be negative 1 over 8 x to the power negative 8. Here that would be 1 over 10 x to the power 10. Here it would be 1 over 9x plus constant. I can bring this x to the power negative 8 here on the denominator, so that I can write it down as a positive. So it would be 1 over 8 x to the power 8 minus 1 over 10 x to the power 10 minus 1 over 9 x plus constant. So that's our final answer. So I don't need this space. Now here we are looking for antiderivative. Before doing this kind of problem, try to simplify this if it's possible. Trig function, sometimes they can be simplified. Cosecant 8 theta over cosecant 8 theta minus sine 8 theta. I'm just going to try to simplify it if it's possible. Cosecant 8 theta is actually 1 over sine 8 theta. I can use the very same thing here, which is 1 over sine 8 theta minus sine 8 theta over 1. So on the top there is a 1 over sine 8 theta, and on the bottom, by making the same denominator, it would be 1 minus sine square 8 theta over sine theta. This sine theta and this sine theta I can cancel out. So on the top there is a 1, on the bottom I'm going to get 1 over cosine square 8 theta, which is basically secant square 8 theta. So after simplification, this is actually secant square 8 theta d theta. So let's go back to that table and try to find out the formula which gives me the antiderivative of secant square kx. Here k is 8 in our case. So the solution would be, it's a 1 over k 10 kx. So I'm going to just copy that formula here. The formula is integration of secant square k theta d theta is 1 over k 10 square k theta plus constant. Let me just go back and double check. It's 1 over 10 k, k means 8 theta, so no square. Okay, so it's not the square, this is not right, so it should be secant square 8 theta d theta is equal to 1 over 8 10 8 theta plus constant. So that is our answer. If you try to find out the derivative of this thing, it would be secant square 8 theta.
Initial condition and particular solution. Let's say you have a integration of some function f of x, and we know that at this point integration it might have many solutions. For example, let's say the integration of x dx, the integration of x, it could be x squared over 2 plus c, that's the constant here. It could be c, could be 1 2 3 4 5, so it could have, you could have infinitely many solutions. Now if we try to plot the graph of this solution, then you might have so many different solutions, so many different answers. Example, when we try to find the integration of 3x squared minus 1, this is the solution, x cubed minus x plus c. Based on the value of c, if we try to plot the graph of this solution here, as you can see here, if c is 0, the value of the solution of this integration is x cubed minus x. And based on different c, there is a different answer. So each of these antiderivative is a solution of the differential equation, this one. So this is your differential equation, meaning what is the function whose derivative is 3x squared minus 1? These are the function. So in general, this is a generic solution, general solution. And if we try to find the particular solution, for example, I'm interested to find the solution of this differential equation where c has particular value, this constant has particular value with some initial condition. So in many applications of integration, enough information is given to determine the particular solution. If you know the value of c, or you know some situation for which you need to find the value of c, that's called particular solution. To do this, the value of this differential equation for one value of x needs to be known. This information is called initial condition. In this example, let's say, for example, in the figure, this figure, only one curve passes through the point 2 4. So this means when x is 2, the value of the function is 4. So that means I can write down this information like this. When x is 2, the value of the function has to be 4. This is called initial condition. Using this initial condition, if I try to find the value of c and plug that value back here, that's called particular solution. So when x is 2, what is the value of function? That's 4. I put that thing here. When x is 2, the value of the function is 4. So I'm going to put x equal to 2 here. That gives me 2 cube, which is 8 minus 2 plus c. And if I try to solve for this constant c, if I try to simplify this here, you can see here 8 minus 2 is 6 plus c. What is the value of c? Just subtract 6 from both sides, and eventually that gives the value of c is negative 2. So now this solution, this function f of x with this constant x cubed minus x minus 2, that's called particular solution of this differential equation.
Now, so sometime they give us a derivative of a function. They also give us a situation like this. The value of that function at 0 is 2. Find out the value of that function. S is the function of time here. So this is the derivative of S with respect to time. And you want to find out the S. So that means from the derivative, you want to find out the function. So that means you want to find out the antiderivative. So antiderivative of this one is, so you want to find out the antiderivative of -4, which is -4t, plus antiderivative of cosine t, which is sine t, plus some constant. Look at here. The derivative of this function is -4 plus 5 cosine t plus 0. That's the same thing. Look. So if you want to find out the function itself from its derivative, that means you are finding the antiderivative. But we also have given one situation. When t is 0, the value of the function is 2. So when t is 0, this part is 2. So if t is 0, then what happens to this part on the right side? It will be -4 times 0, which is basically 0, plus 5 sine 0, which is basically 0, plus c. So that means it gives us the value of constant, c equal to. So now for this situation, the constant should be always 2. So the function, s of t would be -4t plus 5 sine t plus 2. So that is the function. If we try to find the derivative of this function, that will be this. Okay, and then if you try to find out the value of the function at 0, that would be 2. So this is how we can find the antiderivative.